quantum mechanical model or the quantum mechanical theory describes what the electrons are doing, how they're behaving within the atom. And so what quantum mechanics says is that the electrons that are in atoms exist within orbitals. And how those orbitals are occupied by electrons is called an electron configuration. It's like a shorthand notation of these are where the electrons are in this particular atom. And so for something like hydrogen, which is a very simple atom with one electron, the electron configuration is also very simple. There is one orbital that has any electrons in it. It's the 1s orbital. And as a superscript, we give the number of electrons that are in that orbital. If we use Schrodinger's equation and do some heavy-duty calculations, we can find out that the hydrogen's one electron is going to occupy the lowest energy orbital that's present in that atom. We can solve Schrodinger's equation for hydrogen. We can't get exact solutions for multi-electron atoms, so everything else. That doesn't mean that it isn't a good equation. We can still get approximations, which are very, very useful. The reason we can't solve it is because there are additional terms that need to be added in for the interactions between electrons. In hydrogen, there's only one electron. He has no one to interact with. In helium, you've got two electrons. They interact with each other, and that tweaks the equation. And the equation gets tweaked differently for every atom, for every type of element. But the approximate solutions show that the orbitals in these multi-electron atoms are similar to those in hydrogen. The two things that we have to think about with these other elements is electron spin and energy splitting of the sublevels. So we'll be looking at that. Electron configuration is a way to represent how the orbitals are filled. Another representation is orbital diagrams. This is a little more visual. We use boxes and arrows to indicate where the electrons are and what the orbitals are. So for hydrogen, this is the orbital diagram. Here we have a box representing the 1s orbital, and there's one electron in it. And we usually give it an up arrow. There's an up arrow and a down arrow because we have spin, that fourth quantum number. It's either plus 1/2 or minus 1/2. And so just by convention, we call an up arrow plus 1/2 and a down arrow minus 1/2. If you take a bunch of hydrogen atoms and look at the spins of their electrons, you'll find that about half of them are up and half of them are down. So why do we represent hydrogen as being an up arrow? Well, it doesn't really matter which we pick. Some are up, some are down. In hydrogen, it just doesn't really matter. So we just start with up and then we go down. The Pauli exclusion principle tells us that no two electrons in an atom can have the same 4 quantum numbers. Remember, the quantum numbers were the principal number, n, and then there was L and M sub L. L tells us the shape of the orbital. M sub L tells us the orientation. And then that spin tells us, is it have an up spin or a down spin? Is it plus 1/2 or minus 1/2? So you can have 2 electrons in the same orbital. They can have 3 identical quantum numbers, the first 3. But the fourth number has to be different. So we have to have a plus spin and a minus spin. Without talking about quantum numbers, we can also express the Pauli exclusion principle as each orbital can have a maximum of only 2 electrons with opposing spins. When they're in an orbital, you have to have one up and one down if there's 2. This reminds me of a historic fort that I visited in St. Paul. It's called Fort Snelling. And they housed troops there back in 1700, 1800s for sure. And they slept in bunk beds, and you can go into the fort and see where these soldiers bunked. And Minnesota winters are mind-bogglingly cold. I mean, I grew up there. I get it. You guys, minus 40 degrees. That's not wind chill. That's the actual temperature. It's minus 40. And these people were living in the 1800s in, stone buildings or log cabins. They didn't have furnaces. They didn't have down comforters. Somehow they survived. One of the things they did is two guys would sleep in one bunk. And it wasn't a double or a queen-size bunk. It was not even as big as a twin-size bunk. And what they would do is they'd sleep head to toe because they fit better that way, right? Because your legs don't take up as much space. So it was 2 soldiers per bunk. They had to sleep head to toe because otherwise there wasn't enough room. That reminds me of these electrons. 2 electrons in an orbital, they have to have opposite spins so that they'll fit together. I don't know if that helps you or not, but there's my little personal memory. If we know the number of orbitals in a sublevel, then we can figure out how many electrons are in the sublevel. Each orbital can hold a maximum of 2 electrons. The S sublevel has 1 orbital. Do you remember how we know that? What's the quantum number that tells us the shape? It's L. And so for the S, L equals 0. What are the possible values then for M sub L, which tells us the individual orbitals, the orientation? It can go between minus L and plus L, including 0. So if L is 0, there's only one possible number, and so we have M sub L equals 0. There's only 1 orbital. That 1 orbital can hold 2 electrons. In the P sublevel, L equals 1. So I'm going to do this. I should do it for more than just one thing. L equals 1. And so then we have possible values of M sub L, minus 1, 0, and plus 1. 3 orbitals. 2 electrons in each, 6 electrons. The D sublevel has 5 orbitals, so we get 10 electrons. The F has 7, and we can get 14 electrons. Let's look at the quantum numbers for the electrons in the helium atom. So helium has 2 electrons, and they're going to be in the lowest energy place that they can be. So that's going to be the first energy level, quantum number n equals 1. So they're both in n equals 1. In n equals 1, there's only one possible value for L. When L is 0, we call that an s orbital. And there's only one possible orientation, so they're going to have the same m sub L number. You can't have 2 electrons that are described by the same 4 quantum numbers. Every electron has its own combination that describes it. It's like you can't have 2 people with the same social security number. It wouldn't work out very well if there were duplicates. So that means one of these has to be plus 1/2 and one has to be minus 1/2. In the orbital diagram, we indicate the spin. We have one that's pointing up and one that's pointing down. We do not indicate spin in the electron configuration. Any questions yet? So I said that in multielectron atoms, we have interactions between the electrons, and the sublevels end up getting split in energy. In hydrogen, all the sublevels in each principal energy level have the same energy. So hydrogen only has 1 electron. In the ground state, that electron is in the 1s orbital. Other orbitals exist, though. They're just unoccupied. There's a 2s, and there's the 2p subshell. There's a 3s and a 3p and a 3d. In hydrogen, the 3p, the 3s, the 3d, they all have the same level because they're in the same principal shell. But in multi-electron atoms, that's not the case. So for hydrogen, the energy of the orbital depends only on n. That's part of why the Bohr model worked, because you just had these orbits, and the electrons were in the orbit. Degenerate is a word that we use to describe orbitals that have the same energy. When you have more than one electron in the atom, then the energies of the sublevels get split. In the second level, the s and p orbitals don't have the same energy. It gets split, so they are not degenerate. And this is caused by a couple of things: charge interaction between the electrons, shielding, and penetration. In general, though, the lower the value of L within a principal level, the lower the energy of the orbital. So if you're looking at, say, the fifth level, n equals 5, the S subshell will be lower in energy than the P, and then next will be the D, and F will have the highest energy within n equals 5. So we need to revisit Coulomb's law. Coulomb's law says that the potential energy of two charged particles depends on their charges and on their separation. Okay, these are supposed to be subscripts, not superscripts. So here's the full equation. E equals 1 over 4 pi epsilon sub 0. This is all a constant. These are the things that could change: the two individual charges and the distance that separates them. So if the charges are the same, or the same sign, if we've got +1 and +1, then E is positive. And that means that the charges are repelling each other. If we have opposite charges, a plus and a minus, then E is negative, and the charges will attract each other. As the charged bodies get closer together, the potential energy increases. So if you have +1 and -1, as R becomes smaller and smaller, E becomes more and more negative. And the sign here is difficult to get your mind around. But a negative energy means, compared to how they were before, their energy has been lowered. So this is a more restful state, if you will, for the electrons. And so they're going to be attracted to each other. The further apart they are, the less negative that charge is. And the same happens with like charges. If both of these are positive or both of these are negative, now E is a positive, and that repels them. The closer they are, the stronger the repulsion. The further away they are, the weaker the repulsion. If you think about magnets, if you have a North Pole and a North Pole and you try to squish them together, they resist, don't they? And the closer you get, the more they resist. Coulomb's law has applications in magnetic fields as well. Put a magnet on a refrigerator, assuming it's not stainless steel, and you stick one piece of paper under it, fine. Add another piece of paper. Depending on how strong your magnet is, you get a couple of pieces of paper between the magnet and the refrigerator, it won't stick anymore. It's because the distance between the magnet and the refrigerator is getting larger each time you add a piece of paper. And when it gets to a certain point, it won't stick anymore. As the distance increases, the strength of the attraction or repulsion decreases. And that's an important concept to understand about charges. This has application for electrons. So we have, in a multi-electron atom, we have attraction of the nucleus for the electrons. The nucleus is a positively charged thing, and the electrons are negative, and so there's an attraction between them. We also have repulsion between electrons, because all the electrons have a negative charge, and two negatives repel each other. So those repulsions reduce the attraction of the nucleus, and we say the nucleus is shielded, or the electron is shielded from the nucleus. The total amount of attraction that an electron feels for the nucleus is called the effective nuclear charge, and it's given the symbol ZEFF, ZEF. So if there weren't the other electrons, you would expect a force of attraction between the electron and the nucleus that's dependent on the charges and the distance. But because there are other electrons in there, they kind of block some of that attraction. And so we have to look at the effective nuclear charge. And I've got pictures coming up here somewhere, I'm pretty sure, yeah, okay. The other concept is penetration. So shielding affects the observed charge on the nucleus. So maybe the nucleus has 10 protons in it, but because of shielding, this electron is only experiencing a +8 charge. So that's going to reduce the attraction. Penetration is the other idea. This has to do with the distance. The closer an electron gets to the nucleus, the more attraction it experiences. So the better an outer electron is at penetrating into that electron cloud of the inner electrons, the more attraction it will have. The closer that orbit is to the nucleus, the more attraction it will have. And the degree of penetration is related to each orbital's radial distribution function, which we talked about in the last chapter. So here's an illustration that hopefully will help make sense of this. So here we're looking at lithium. 3 electrons, didn't mean to do that. 3 electrons, 3 protons. So we got 3 protons in the nucleus. We don't care about the neutrons for this. There's a +3 charge. There are 3 electrons. These 2 electrons are in an orbital that's close to the nucleus, and this electron is in the next energy level, which is further away. So the way I think of this is these guys are closer. These guys basically cancel out 2 of the charges here, because you've got these 2 electrons in here, and so they are kind of taking care of 2 of the plus charges on the nucleus. What's left for this one to see? +1. So this has an effective nuclear charge of about +1, because these guys are closer in. They're getting in the way, if you will. They're shielding this electron from the nucleus. So their shielding is approximately equal to their number of charges. So these inner electrons, there's 2 of them, so they shield 2 of the protons so the other electron can't see them. Penetration happens when this electron is able to get in to this area. Now these electrons are not between this electron and the nucleus because he's down in there with them. And so he gets the full +3 charge. Does that make any sense at all? No? I've got some yeses and some nos. There's an analogy in here somewhere. My analogy maker appears to be on the fritz this morning. Let's try looking at it this way. So here we have our +3 nucleus. Let's think about the Bohr model. So in this first energy level, there's these 2 electrons. And in the Bohr model, these guys are going around. And they're moving pretty fast, actually. They're going around. And then out here, we have another electron. So this electron is looking towards the nucleus, trying to get attraction here. These 2 guys are spinning around. 2 negatives are between it and the nucleus. And so these basically wipe out 2 of the positive charges here. And so what this one experiences is only +1. Each of these experiences +3 because they're the same distance away. This one is not getting between this one and the nucleus. They're just going around together here. This illustration over here, we've got the same 3+ nucleus, and we've got those same 2 electrons in that level. But now this guy is joining them in here. So now he's in that level as well. He's able to penetrate into their space, and so there's nothing between him and the nucleus now. Does that help at all? I have to come up with a better analogy for that one. Yes?
How can 3 electrons be in the same orbital?
Well, they can't be in the same orbital. We'll get to that. Yeah, you're right. They can't be in the same orbital. In fact, we'll get to it right now. So we looked at those radial distribution functions, right? So here's the 1s orbital. 0 radial probability at the nucleus, goes up really high and comes down quickly. The 2s has a nice little bump of probability in here, and then a node, and then another big bump out here. So most of the electron density for the 2s electron is out here, but some of it is in here in the same space, the same distance from the nucleus that's occupied by the 1s. So the 2s has some penetration into the space of the 1s. These orbitals can occupy the same space. Orbitals are kind of like a standing wave. And so if you look, we looked at the string video with the waves, the standing wave. And when you look at that constructive interference area, you see, well, how do you say the wave is here or the wave is here? It's in that whole area at the same time. It blurs together. And so this is like a standing wave, and we've got a node here, and we've got a peak here and a peak here. And so this part of the 2s electron, 2s orbital, is in the same region of space as the 1s orbital. So this 2s electron experiences more attraction from the nucleus than the 2p electrons do. The 2p penetrates a little bit here as well, but the distance is really, really important. It's more important. And so this one can get much closer. Does that make any sense? Yes. Questions?
Is it kind of like you took a snapshot picture, occasionally those electrons be close to the nucleus, and most
Yes.
of the time they do like.
Yeah. So if you were taking the multiple exposures for these different orbitals, oh, that's not what I wanted. So if this is the P, we're going to see, the 2s. More often we're going to see them out in this region, but sometimes they're going to be in there close, just as close as the 1s electrons are. And so it penetrates in, and it has more attraction than the 2p. The 2p doesn't get in this close, just very, very rarely. So the 2p has less penetration than the 2s does. So the 2p electrons are more shielded than the 2s electrons. This causes a difference in the energy level of those two subshells, even though n equals 2 for both of them. Because the 2p has less penetration, it's going to have less attraction for the nucleus.
So if they have less penetration, they have more shielding.
Right. Penetration gets around shielding. If you don't have penetration, you experience all of the shielding. The more penetration you have, the less shielding you experience. So they're kind of opposing forces. So it's because of penetration that the sublevels are not degenerate. When we get to the 4th and 5th principal levels, the effect of penetration becomes really important. Remember, as the principal quantum number increases, the difference between those primary levels becomes less and less. And so then small differences become more significant than between the 1 and the 2. So penetration and shielding get so important for these that you actually get 4s orbitals being lower in energy than the 3d orbitals. And things get all kind of jumbled up because the energy separations are getting smaller and smaller. And just to add into the mix of confusion, the relative energy ordering can actually vary among elements. We're not going to worry about that, but I want to tell you that it does happen. So here's the general energy ordering. You're like, what the heck are we looking at? So low energy down here, higher energy up here. Remember, these are like teenage boys. They want to go to a lower energy state. So if you've got an electron coming in here, deciding which orbital to be in, it's going to go to the lowest one that it can get into. So it'll go in here. And next is the 2s, and then there's the 2p. And this difference here is because of the penetration of the 2s. Otherwise, the 2s would be up here. This is what we see for a 1 electron atom like hydrogen is the 2s orbital has the same energy as the 2p. But because of the shielding caused by this one, these are not the same. And s penetrates more, and so it can get in. Then we have 3s and 3p and 4s, and that's all going according to what we would think. And then things get a little funky because the 4s is actually lower than the 3d. And then next is 4p, 5s, and 4d. And so there's different ways to remember what that order is, and we're not going to get to that today, but it's actually all hiding on the periodic table. And so just hold on and we'll get to that. There is a process of filling orbitals. It's called the Aufbau principle, building up. So when we put electrons into orbitals, and of course, we don't put electrons into orbitals, right? This is us trying to figure out where the electrons actually are. So we talk about putting them into orbitals, but they're just there and we're describing what we've observed. The electrons are going to go into orbitals to minimize the energy of the atom. They're going to fill up the lowest energy ones first. Here is another filling order. This is the filling order just written out, 1s, 2s, 2p, 3s, 3p, 4s, etc. We have to remember that orbitals can hold no more than 2 electrons each. The spins have to be opposite. And then, as if there aren't enough rules yet, Hund's rule says that when you're filling degenerate orbitals, the electrons fill them singly first with parallel spins before they pair up. Well, this is like people getting on a public bus. I used to ride the bus when I was in college. You get on the bus, and there's several seats with one person in them. You don't know any of these people. And then there are several seats that are empty. Are you going to sit with a perfect stranger when there's an empty seat and you could sit by yourself? No, of course not. Unless maybe he's really, really cute and you're feeling really aggressive or something, but electrons don't do that. You're going to take your own seat. That's what the electrons are going to do. If they've got 3 orbitals to choose from and the first one has somebody else in it, they're going to take their own orbital. So that one's not too hard to remember. Here is another way of remembering this orbital filling. This makes a lot of sense for some people and just not at all for other people. So I'll show this to you, but don't feel like you have to use it. Like I said, I just look at the periodic table. It's all right there. You write these out, 1s, 2s, 2p. See, the first level has 1. The second level has 2. The third level has 3. The fourth level has 4. And we're just not even going to talk about what happens after F. But what you do here is you start drawing diagonal lines. So 1s fills first, and then you're jumping back up here. And next is the 2s, and then 2p and 3s, and 3p and 4s, 3D, 4p, 5s, etc. You get the idea? So if that works for you, awesome. If not, ignore that. When we talk about writing electron configurations, unless it's stated otherwise, we are assuming that we're talking about the ground state. Each atom has one ground state, with electrons all in their lowest energy configuration. There are many excited states. Many, many, many excited states. It's helpful to remember that the number of electrons in a neutral atom equals its atomic number. All the atomic numbers are on the periodic table. So if you need to draw the electron configuration for krypton, well, you find krypton, it's element number 36. That means you have 36 elements to place, 36 electrons to place. Good grief. Does anybody wonder how, because we're talking about negative things, two negative things like two electrons would repel each other, right? So how can two negatively charged electrons occupy the same orbital? Does that bother anyone? It bothers me. It's because of the spin. When they have parallel spins with correlated motion, it minimizes the mutual repulsion. So when you get these 2p orbitals and you've got electrons in each of them, the parallel spin helps them to not repel each other. Then each orbital can only have 2 electrons, and we kind of went over that already. So when we write an electron configuration, it's a listing of the sublevels in the order of filling with the number of electrons written as a superscript. So for example, chromium, I am just like really off this morning. Krypton has 36 electrons. So they will be in these orbitals. 1s2, 2s2, 2p6, because there's 3p orbitals, they each hold 2 electrons. So those are going to fill up. Then 3s2, 3p6, 4s2, 3d10, 4p6. If you take all of these superscripts and add them together, they add up to 36. So that can be a check when you're writing an electron configuration. Add up the superscripts and make sure that they add up to the number of electrons you have. You can also use that if you've got an electron configuration, you need to figure out which element it is. Well, just count up the number of electrons and that'll tell you which element. This gets really tedious after a while. You know, here's rubidium. It's just a lot of things to write, and this stuff at the beginning is all the same. So there's a shorthand. Sometimes it's called an inner electron configuration or the noble gas configuration. That's my preferred term for it. We use the symbol of the previous noble gas in brackets to represent all of the inner electrons. So if we look at rubidium on the periodic table, it's over here, right? Period 5. It has 1 more electron than krypton. So what we do, instead of writing out all of this mess, we write krypton in brackets. What we're saying is the electron configuration of krypton plus this. It's so much shorter. So let's look at a few elements here. Here's lithium, has 3 electrons. Personally, I prefer to look at orbital diagrams first and then electron configurations. So the orbital diagram, the lowest energy orbital is the 1s orbital. And so we're going to put 2 electrons in there. Like the soldiers in the bunk beds, they have to be opposite spins. And then the 3rd electron has to go into the next higher one, the 2s. And so we abbreviate that as an electron configuration, saying 1s has 2 electrons, the 2s has 1 electron. This is a situation where chemists do write the number 1. In beryllium, 4 electrons. Well, this was 3 electrons. The 4th electron is going to have to bunk with this electron in the 2s, because they don't want to go up to a higher energy level if they don't have to. So we're going to get 1s2, 2s2. For boron, 5 electrons. Well, 1s and 2s are full. So the 5th electron goes to the next sublevel and takes one of these. Just by convention, we always draw up arrows first. In carbon, we see an example of Hund's rule, which is this parallel filling. Because here's the bus, and electron number 6 is going to get on this bus, and well, these seats are full. Is he going to sit with this electron, or is he going to take his own seat? He's going to take his own seat. And so these guys will be spread out. The orbital diagram gives us a little more detail than the electron configuration does. The electron configuration for carbon is 1s2, 2s2, 2p2. And 2 plus 2 plus 2 equals 6. Any questions? Okay. So here's one of my stupid analogies. The quantum hotel. It's a discount resort for electrons in Mrs. K's Chemistryland. Chemistryland may not be the happiest place on earth for you, but I like it a lot. This is not a scientific analogy, but these orbitals and sublevels and things are hard for students to grasp. They're very abstract. But I see parallels between this order and what happens in a hotel. It's kind of a strange hotel, but I think it'll make more sense than all that gibberish I was just spouting at you. So in this hotel, it's kind of it's an inverted pyramid. You wouldn't want to build this in California because it would kind of tip over. But it's like those crazy hotels you see in Las Vegas. You know, there's one that's a pyramid. This one's an upside down pyramid. So the bottom floor is the smallest, and the floors get bigger as you go up. The first floor only has one room. And they don't number the rooms, they give them letters. So on the first floor, we have an S room. On the second floor, there's 2 rooms, the S room and the P room. On the third floor, there's 3 rooms, S, P, and D. How many rooms are on the 4th floor? 4, S, P, D, and F, right? It's their hotel. They can do anything they want. Okay, so these are kind of strange hotel rooms. The S room has 1 bed. Okay, that's cool. P rooms have 3 beds. Not too many hotel rooms have 3 beds. The D rooms have 5 beds. I would love to find a hotel room that had 5 beds. That would be awesome. The F rooms have 7 beds. Why? Because that's how they built the hotel. Just get over the why. So it's important to understand some of the rules that they have in the hotel. Only 2 people are allowed per bed, and they must have opposite spins. Now, you can, whatever analogy works for you on the spin, you can think of the soldiers. You know, if all of the electrons are male and they're coming in, guys don't like to share beds for the most part. They'd rather sleep on the floor, but you're not allowed to sleep on the floor, so they're going to avoid any possible issues by sleeping head to toe. So that would be opposite spins. Another way to think of it would be gender or sexual orientation. 2 people sleeping in the bed have to be of the opposite whatever. Okay, so whatever works for you. So in this analogy, the floor is equivalent to the principal shell. The first floor is n equals 1. Each room is a subshell. The S, the P, the D, the F, subshell. Each bed is an orbital, each person is an electron, and energy is related to money. Why does the first electron take the 1s room instead of the 2s room? It's cheaper. He doesn't have to pay as much. The 2s room costs more. The 2p room costs even more than the 2s room, and so on. Any questions? So then I see this as kind of a picture of this crazy hotel. right? So it gets wider at the top. Maybe this is the elevator over here. So the first floor, there's only one room. The second floor, there's two rooms. And the difference here in the height is the cost. You know, when you go to a hotel and you're comparing, we did some traveling this summer, and I went on TripAdvisor, and you're comparing all these different rooms and all these combinations. It really doesn't make a lot of sense, does it? The hotel just decides, we're going to charge this for this room and this for that room. And you're like, you take it or leave it or go somewhere else, right? So they charge less for this room than that room. This one's more, then this one, then this one. These rooms are less expensive than those rooms because hotel management decided it was so. There's no other explanation. So if you think about electrons, people coming in and staying in this hotel, let's say we had 7. Let's say we have 8 people staying in the hotel. And so I'm going to draw them as little arrows. So the first person, he's like, well, I'll take this room because it's cheaper. The next guy comes in, and his options are this room that's cheaper, but he has to bunk with this guy, or he can pay more. This is a discount resort, okay? These people are trying to save money, so he's going to take this one. And then the next one comes in. He's going to take the cheapest room. The next one comes in. He's going to take the cheapest room. Okay, the 5th one comes in. He has to go to this more expensive one. The 6th one comes in. This room has 3 beds. Each of these lines is a bed in this room. Is he going to sleep in the same bed with that guy when there's 2 empty beds? No. Is he going to sleep upside down in that bed? No. So then the next one comes. He's also going to take his own bed. Number 8 comes in, and all the beds have 1 person in them. But cheapness is the most important thing. He's not going to go up here so he can have his own bed. He's going to pick one of these. The rules are you have to be opposite spin. So he's going to sleep upside down in the bed. Does that make a little more sense of how you would do this? It's really stupid, but it works, doesn't it? Because it's like, oh, okay, well, there's some logic that I'm familiar with now. I can kind of visualize this. Of course, electrons are not taking beds. They're not thinking about stuff. But this helps us to make sense of the patterns we observe. So let's write electron configurations for each element. Actually, let's skip to this one because I like orbital diagrams better. We'll do this one, then we'll go back. Write an orbital diagram for argon, and then figure out how many unpaired electrons it has. First thing we need to understand is how many electrons does argon have? Argon has 18 electrons. So what I'm going to do is I'm going to draw, because it's an orbital diagram, I'm going to draw boxes. And so here we have the first floor of the hotel. That was the 1S room. And I'm going to draw them in order of increasing cost, increasing energy. The next one is 2S. The 2P room has 3 beds, so I'm going to represent that as 3 boxes that are together. So we got 3 boxes. That's the 2P room. And then next will be the 3S, go up to the 3rd floor. And after that is the 3P. Next would be 4S, but it turns out we're not going to have to go there. So I've drawn my beds in my rooms, and now I'm going to put my little electron people in them. And I'm just going to count as I do it because I can't visualize 18. So we got 1, 2, 3, 4. In this one, they're going to take their own bed first. 5, 6, 7. Now they have to pair up. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. How many unpaired electrons are in here? None. So this is the orbital diagram, and the other question is determine the number of unpaired electrons. 0 unpaired electrons. The electron configuration I see as what the hotel clerk keeps track of as people check in, so he knows where to send the next electron. So the electron configuration for this would be 1s2, 2s2, 2p6, 3s2, 3p6. I'm just writing down the designation of the subshell and then how many electrons are in it. The resort rooms, the hotel rooms, and how many people are in each. Any questions? Let's go back and do these other guys. Electron configurations. Okay, so for chlorine, how many electrons does chlorine have? 17. 17 electrons. So we're going to try to do this without drawing orbital diagrams. Well, the first room was the 1s. How many electrons can go in that? 2. Next is 2s, and how many can that hold? 2. So we're up to 4. Next is 2p, that can hold 6, and we got 10 electrons. Next is 3s, that can hold 2. We're up to 12. We've got 5 left. The next room is the 3p, and so we can put all 5 of them in there. Electron configuration for chlorine. We could abbreviate this. So we see chlorine on the periodic table. Go up 1 row. Previous period, what's the noble gas at the end? Neon, right? This is the electron configuration for neon. So the noble gas shorthand is, instead of writing all of that, I'm going to just write neon in brackets, and then I'm going to write the extra stuff after. So neon plus 3s2 and 3p5. Let's do silicon. How many electrons? 14. So they always start out the same. So after a while, even if you don't try to memorize it, you'll remember it. 1s2, 2s2, 2p6. You have to stop and count every once in a while. Okay, I'm up to 10. And have four more. 3s2. That's 12. 2 more. They're going to be in the 3p. Any questions? So strontium, how many electrons does strontium have? 38. Fun. Okay. 1s2, 2s2, 2p6, 3s2, 3p6. We just did this guy up here. That was 17, so I got 18 right now. I need 20 more. Okay, 3p6. Next is 4s2. And then after the 4s comes the 3d. How many electrons can fit in the d level? 10. So now we better count. 10 and 20. We're at 30. We need 8 more. After the 3d is the 4p. So that's going to have 6, and then comes 5s, and that's going to have 2. What's the noble gas shorthand for strontium? be krypton in brackets, plus what? Just the 5s2. Same electron configuration as krypton with the addition of this 5s2 business. Okay, how about oxygen? How many electrons? 8. 8 electrons. So 1s2, that's 2 electrons. 2s2, that's 4 electrons. We need 4 more, or 2p4. That just seems anticlimactic after strontium. Questions? Did that one?